Hello again and welcome. My name is Peter Christensen, and this is the second of two sessions that I'm recording on the topic of matrices. I hope you enjoyed the first session where we looked at an intuitive understanding of why matrices are used and how they can be helpful. If you haven't seen that session yet, I suggest that you go and look at that now and then come back and we'll carry on. Oh, you have seen it? Oh, okay, well let's carry on. Well, you may recall that in that session we looked at a scenario called Peter's Cafe, and in that scenario we discovered that it makes sense sometimes to want to add matrices together, and it makes sense to want to multiply them together, and the calculations that are required to do that give us information that's useful, particularly with adding up a bill. Well, in this particular session what I'd like to do is continue on with some matrix theory, which we will derive from the scenario that we looked at in terms of matrix addition and multiplication, and then we'll look at finishing up by examining what we've discovered so far and how we can use that to solve a practical problem. So I'm hoping you're feeling refreshed and ready to go. So let's take a look now at different types of matrices and the terminology that we use when we're trying to describe them. So in the bottom right hand corner I've put here a set of matrices, which I thought if you've never seen a matrix before it might be helpful to see one, and you'll notice that they come in all sorts of shapes and sizes, and in particular every matrix has got a certain number of rows and a certain number of columns, and we classify a matrix according to its dimensions. So we notice that matrices have dimensions, and we usually classify them as an m by n matrix, where m is the number of rows and n is the number of columns. So if I said we had a 5 by 7 matrix, then we would know it had 5 rows and 7 columns. So if you've got the same number of rows and columns, we talk about having a square matrix. So here are some square matrices. It's pretty obvious why they are square, because when you see them they look like squares rather than, long rectangles. If you've got more rows than columns, then we talk about having a skinny matrix. So here are some examples of some skinny matrices where the number of rows m is more than the number of columns. And you could guess that if it was the other way around, if we had less rows than columns, then we'd have what's called a fat matrix. So it seems pretty non-technical names to give to matrices, but really they're helpful descriptions, and sometimes that's all you're really wanting, is to just get a description of the shape of the matrix before deciding how you should handle it. The next thing to look at is if the matrix has only got one row where the number m is equal to 1, one of its dimensions is equal to 1, then we talk about it being a row vector. So a vector is just a matrix where one of its dimensions is equal to 1. If it's the row that's equal to 1, we call it a row vector. And you could guess if it was the column that was equal to 1, then we'd call it a column vector. And it's usual not to bother about calling them row vectors and column vectors unless there was going to be a distinction made between whether we're working with columns or rows. So if you hear someone just talking about a vector, it probably doesn't really matter if it's a row vector or a column vector, but if you're specifically talking about a row vector, you know that it's probably somewhere going to get confused later on with a column vector if one happens to show up, or the other way around. Matrices are usually given capital letter names like capital A, capital B, etc. And you could describe a couple of matrices here. Here's one. Let A equal 1, 2, 3, 4, and let B equal 4, 1, 8, 9, 6, 2, 5, 0. Now I can tell you straight away it's pretty easy to tell that A is a 2 by 2 matrix, but can you tell the dimensions of B just by looking at it? Well, is it a 2 by 4 or a 4 by 2? Can you remember? Well, it's got 2 rows, and we usually say the rows first. So B is a 2 by 4 matrix. Now vectors are given lowercase names, so it's quite common to see vectors written like a little v, probably for vector, or a little w, or anything with a small letter next to its name is usually used for matrices that have only got one row or one column. It's not mandatory, but this is what is usually used for convention. Now be aware there's such a thing called a zero matrix. It's usually given the name capital O, and it makes it look like a zero, which is quite handy because the zero matrix can behave a lot like the number 0. It's pretty harmless. It doesn't do anything. If you add the number 0 to a number, it doesn't actually change the number. Well, the same thing with a zero matrix. If you add a zero matrix to another matrix, you'll end up with just the first matrix that you started with. It doesn't change it. However, be aware that it will destroy another matrix if you multiply it by a zero matrix, just like the number 0. So here are some examples of what a zero matrix might look like. Again, it could be any dimension, all shapes and sizes. The only thing to notice that every single element of the matrix is a 0. So the dimensions will vary according to the context, but if you take a matrix and add a zero matrix to it, you'll end up with the same matrix that you started with. Now, the next thing to notice is there's such a thing called an identity matrix, and it's usually given the name I, or capital I, for identity, but it's quite handy because the I looks a bit like the number 1, and the identity matrix behaves a bit like the number 1. If you multiply a matrix by the identity matrix, it doesn't change the matrix that you started with, just like the number 1 won't change a number. If you multiply any number by the number 1, you end up with the number you started with. So it's a pretty harmless sort of a matrix if you're going to be multiplying by the identity matrix. Now the identity matrix is always a square matrix, and it has got 1s on the diagonal and 0s everywhere else. So you might have been excused for thinking that the identity matrix might have 1s everywhere, because if you remember, the zero matrix has 0s everywhere, so why not have the 1s everywhere in an identity matrix? Well, it just so happens that if you were to play around with trying to multiply matrices using one of these identity matrices, you'll soon see that you'll end up with a matrix which is just exactly the same as the matrix that you started with, and so therefore it behaves like the number 1. Again, the dimensions for an identity matrix vary according to the context of how you're trying to use it. So it depends on the size of the matrix that you're trying to work with as to the size of the identity matrix that you're going to need. Now let's look at matrix addition. If you've got a few matrices there, A, B and C, I've got A is a 2 by 2, B is a 2 by 2, C is a, now is it 2 by 2 or 2 by 3 or 3 by 2? It's 2 rows, that's the rows first, 2 by 3. Okay, so let's look at what does it mean to say A plus B, the matrix A plus the matrix B. Well, if you remember our Peter's Cafe scenario, we did some matrix addition then where we said, look, here's the quantities bill from last week and the quantities bill from this week, and we said that, you know, John had a cup of coffee last week and he had a cup of coffee this week, so we'll add the corresponding entries and we'll say he had 2 cups of coffee this week. Well, it's the same sort of thing. We can pretend any matrix is just like a quantities matrix where we add up corresponding elements. So in this example here, you've got a 1 in the top left corner and a 4 in the top left corner. So we're going to have to add those together to give the new element in the sum matrix there. So this is how we do it. We just basically say, okay, 1 plus 4, top left corner is a 5, so in the top left corner we'll put a 5 for our solution. Bottom left corner, we've got a 3 and a 6, we'll add those together and that'll be a 9 in our bottom left corner, and so on. We can complete the matrix like that. Okay, so that's how we do matrix addition. We just basically match up corresponding elements in each of the two matrices that we're trying to add. Now what about doing it the other way around? What if we said B plus A? It's the same two matrices. Does it really matter which order we put them in? Well, just like numbers, no it doesn't. We can take the first one and add the second one to it. You'll notice our calculations are back to front. We're adding 4 plus 1 instead of 1 plus 4. But with ordinary addition, it doesn't matter which way around they go, and the same with matrices. You'll end up with the same matrix 5, 3, 9, 6, which happens to be the same as the first calculation we did for A plus B. So we've got B plus A equals A plus B. Nothing special about it, but what we can say about that is that matrix addition is commutative. That's a funny word. Like, I commute to work every day, I catch the train there and I catch it back. I catch it there, I catch it back. I go one way, I go the other way. So commutative is a word that basically means it doesn't matter which order you go. You can go A plus B or you can go B plus A. You're going to end up with the same thing in the end. So basically for addition, order doesn't matter. But what does matter is that matrix addition only applies when the matrix dimensions match. So you notice that for A and B, they're both 2 by 2 matrices, and because they're the same size we can add them together. But the idea of adding A plus C is meaningless because C is got different dimensions altogether than A. So you couldn't really add A plus C. It just wouldn't really work. You'd run out of, if you're trying to pair up the numbers to add, you'd run out of pairs. So be aware that there are some restrictions on how we add matrices. Okay, now let's look at matrix multiplication. Assuming we've got those same three matrices, A, B and C, what does it mean to say A multiplied by B? We use a little X symbol to show multiplication for matrices, the same as we do for numbers. But do we just multiply corresponding elements like we did for addition? Well, if you remember back to the Peter's Cafe scenario, you'll remember that the matrix on the left hand side represented the quantities of cups of tea and coffee and sugar and biscuits that were ordered, and the matrix on the right hand side represented the price list for those quantities of items that were being sold. So what we did when we multiplied there was we actually took the full row on the left hand matrix and we multiplied it by the full column on the right hand matrix. And so it wasn't just a simple matter of matching up item by item, and it looked more like this. We took the first, let's pretend like this was, John had 1 cup of tea and say 2 biscuits, and the price of a cup of tea was say $4 and the price of biscuits was $6. That's a pretty silly example, but it shows you that the way we calculate when we multiply matrices together is we take the first row, so we take the 1 and we multiply it by the first column, so that'll give us 1 times 4, and then we'll add that to 2, which is 2 biscuits, times the cost of a biscuit, $6, so 2 by 6. So basically we end up with the number 16 for that first entry in our matrix, and so on. So you'll find that there's more calculations involved than when you do matrix addition, but it wasn't too difficult to understand when we thought of it in terms of people in a cafe ordering cups of tea and coffee, and we had a price list that we were comparing their quantities with. Well, now let's have a look at what if we do it the other way around. What if we take, we multiply B times A? Well, normally with numbers, it doesn't matter which way you multiply them as well. If I said 3 times 7, that's 21. If I said 7 times 3, that's also 21. So it doesn't really matter which way we multiply them. However, with matrices, let's have a look. If we take these two matrices and multiply them together using the same technique that we used before, and now this time we're going to pretend like John ordered 4 cups of tea and 1 biscuit, and the price of a normal cup of tea is $1 and the price of a biscuit is $3. Then when we calculate the first entry, it's going to be 4 times 1 plus 1 biscuit times $3. So 4 times 1, it's not going to be the same. In fact, none of those entries are going to actually match the previous entry. You'll have 4 times 1 plus 1 times 3, that's 7. And likewise, the whole matrix is completely different. So that tells us something about multiplying matrices. Notice that because A times B is not equal to B times A, we can't say that matrix multiplication is commutative. In fact, it's not commutative, and we have to conclude that order matters. So that's where multiplication of matrices, or matrices, are a little bit different than ordinary numbers. It's probably the first time we've discovered that they're a bit different, because when you multiply them, it really matters which order you do it with, which one comes first. So with that in mind, I'd just like to now talk about when you multiply matrices, what do you end up with? Like, what are the rules between multiplying matrices and their dimensions? So I'm going to refer back to what we looked at last time in the first session and remind us how we had a quantities matrix here where John ordered 2 cups of tea, 2 cups of tea, no cups of coffee, 2 sugars, 3 biscuits, and 3 sugars and a biscuit. And these are the prices for regular customers, and these are the price list for club members. Now we saw that this matrix here had 5 columns, 1, 2, 3, 4, 5, and 4 rows, John, Paul, George and Ringo. So each customer had their own row, and there were 5 items for sale. And we saw that this price list had 5 items in the rows and 2 columns. And the answer that we got when we multiplied those two together was 4 rows and 2 columns. So let's have a look. Let's see if we can formalize what we've got here. We started with a 4 by 5 matrix, and we multiplied that by a 5 by 2 matrix, and we ended up with a 4 by 2 matrix. So where did the 4 come from in this 4 by 2 matrix? The 4 came from the number of rows in our first, or our left hand matrix. Where did the 2 come from? The 2 came from the number of columns in our right hand matrix. Now, to sort of make this a bit perhaps clearer, I've got a set of eyes here. It's a bit spooky, isn't it? Here's my eyes just roaming around, and I want to show you that if I look at this first matrix with my eyes, all I'm seeing for that first matrix is 4 rows. I can't quite see that there are 5 columns because I'm only looking at it side on. If I turn my eyes around and look this way, I can see that there are 5 columns, but I can't quite tell that there are 4 rows. And if I look at this second matrix on the right hand side, I can see that there are 5 rows, but I don't quite know how many columns there are. And if I turn it around this way, I can see that there are 2 columns, but I don't know how many rows there are. So it's like if I could actually look at the number of rows in this first column and the number of columns in this second, and remember that then I'd know straight away what the answer is going to be. It's going to be the same number here and here. Now, if only I could split my eyes and we could have a look at it. Well, let's do that now. I'll just split up my eyes. Bit crazy, isn't it? Really weird. But anyway, let's imagine with one eye I could look at the number of rows in the first one, and with my other eye I could look at the number of columns in the price list. So that's straight away I could look at those two matrices that are being multiplied, and I could tell straight away that the answer is going to be a 4 by 2 matrix in the bill. So what I'm seeing here is going to be transferred the same number into the bill. It's like I'm ignoring the fact that there are 5 columns here and ignoring the fact that there are 5 rows here. I don't really care, because somehow when I multiply them together they cancel out in some way, and they just disappear, and all I'm left with was what I first saw with my 2 little eyes. Okay, keep that thought in mind. I'll take my eyes away from you so I don't freak you out too much. What I like to do now is just pretend like we've changed the menu a bit, and not only am I serving tea, coffee, biscuits and sugar and milk and so on, but I've added a few more items to the menu. Let's say I've now added, let's see if we can do this. I've now added things like muffin, cakes, apples and peppermints. Well, let's say John bought not only 2 cups of tea and 2 milks and sugars and biscuits, but he'd also bought a couple of cakes and a couple of apples and peppermints and so on. So I've got some extra items here, extra elements in my first matrix. Now this matrix still makes sense because it's got 4 rows like it had before, and if I was to guess what the answer would look like, I'd say, well, I'm going to guess it's going to have 4 rows, and I'm going to guess that it's going to have 2 columns in the final solution. However, the problem is it doesn't make sense to be able to multiply these together, because even though I've got 4 and 2, I've got now 9 columns in my quantities matrix, but I don't have enough rows in my price list to correspond when I do my calculation. So I could start by saying that's 2 cups of tea at $2.40 plus 0 cups of coffee at $2.80 plus 2 cups of 2 milks at 30 cents each, 3 sugars at 20 cents each, 1 biscuit at 60 cents each, no muffins, 2 cakes at, well, hang on, I can't multiply it. I'm stuck. I get the 2 cakes and I've got nothing to multiply it by. So there's a problem. The only way to be able to legitimately multiply these 2 matrices is to extend my right hand matrix, which makes sense. Now, if you're going to be charging people for your muffins and your cakes and your apples and your mints, you're going to need to have an appropriate price list to correspond to your quantities matrix. And now we can do the same calculations like we did before. We'll add in all these extra things, so when we get to 2 cakes, we can say that's 2 times $1.70 plus 3 apples at 80 cents each plus 2 peppermints at 40 cents each. So basically we can then come up with a new bill, which is a bill that is quite a sensible looking bill. The thing is, as before, if with one eye I look here and I can see that there are 4 rows, and with my other eye I can see that there are 2 columns, that makes sense now that the total bill will be a 4 by 2 result when you multiply them together. So what have we learned by looking at this now? We've learned that it's okay to multiply things together if they're not the same dimensions. However, the inner dimensions of 1, 2, 3, 4, 5, 6, 7, 8, 9 must match up with the row dimensions 1, 2, 3, 4, 5, 6, 7, 8, 9 rows. So the number of columns here must match the number of rows here. Otherwise, it just doesn't make sense to multiply them together. Okay, so having seen that, let's now consider what it looks like if we were to multiply the matrix A times the matrix C. Notice they're not the same size. A is a 2 by 2 matrix and C is a 2 by 3 matrix. Well, if you could imagine, is it likely that these are able to be multiplied? If they were, I wonder what size matrix we'd end up with. Well, just imagine if you could put one of your eyes looking at the first matrix from the left, you'd probably say, well, it's going to have 2 rows, and with your other eye, stretch it around and look up from the bottom on the right hand matrix, and you'll see it's going to end up with 3 columns. Well, let's give it a try. We'll multiply those together, and sure enough, if you pretend like the one on the left is a quantities matrix, so you could say John ordered 1 cup of tea with, say, 2 biscuits, and the price of the cup of tea is, for regular users, it's $2 plus $1. Then you could multiply that out and you get 1 times 2 plus 2 times 1, that's a total of 4. And then you could work your way across. This is a case where you could pretend like the matrix on the right was a price list that had 3 columns. You could say the middle column, which has got the 4 and the 0, that's the price that I charge if I think you're a scoundrel, and I'm going to charge you double the amount for your tea than I would if you were a regular user. And silly example, but you get the idea that it is quite possible to multiply matrices together even if they're not the same size or dimension. So multiplication is different again to addition, because with addition there'd be no way you could add A plus C, but in this case we can multiply A times C. So now let's notice that the first matrix columns must match the second matrix rows. So before, when we looked at the Peter's Cafe example, we started off with 5 columns and 5 rows, and then all of a sudden I extended the number of columns in my quantities matrix to say that there are now 9 columns. So I couldn't really do anything as far as multiplying them together until I made the matrix on the right hand side, my price list, match with 9 rows. So in this case, A times C is allowed, because if you look at the dimensions of A, it's a 2 by 2, and if you look at the dimensions of C, it's a 2 by 3, and the 2 inner coordinates, if you like to call them that, I'll just flash them there in green, you can see that these 2 inner coordinates are equal, they match. So it's quite allowable to multiply A times C. And when you multiply A times C like we've done there, we'll get a result of a 2 by 3 matrix. So that matrix on the right hand side, which is 4, 4, 17, 10, 12 and 37, that's the result of multiplying A times C. Now, where did the 2 and the 3 come from? Well, that came from where our eyes would be looking. If we looked at with our left eye, we looked at the number of rows from the first matrix, and if we also looked at the number of columns from our second matrix. So we end up with a 2 by 3 matrix. So now also consider that if we would try and multiply C times A and do the reverse, it's not allowed, because you'll notice that C is a 2 by 3 matrix and A is a 2 by 2 matrix. So those inner coordinates for their dimensions, they don't match. And so it's not possible to multiply C times A. It doesn't make sense to do it. Okay, so that's basically the mechanics behind addition and multiplication. Now the next thing to be aware of is that sometimes, but not always, sometimes a square matrix might have an inverse matrix. What do I mean by an inverse matrix? Well, by an inverse matrix I mean if you multiply a matrix by its inverse, if it's got an inverse, then you get, well, hang on, let me stop here and think. I know what an inverse is with normal numbers, like the inverse of, say, 2 is a half, or the inverse of 7 is 1/7. Now when you multiply a normal number by its inverse, you just get, well, 2 times a half, you just get 1, or 7 times 1/7 is just 1. So when you multiply a matrix by its inverse, you get a harmless, do-nothing matrix called the identity matrix I. Now remember we said that I was very much like, behaved like the number 1. So that's how an inverse matrix will work. If you take a matrix and multiply it by its inverse, if there is an inverse, doesn't always have one, but if you multiply it by its inverse, if it's got one, you're going to end up with the identity matrix I. So let's have a look at this. If you take any number and multiply it by its inverse, you get 1. I said 7 times 1/7 is equal to 1. 1,000 times 1,000th is equal to 1. 3 times 1/3 is equal to 1. That works for any number. Aha, not any number. There's one number where it doesn't work for. It doesn't work with 0. Now 0 is destructive and has no inverse, because if you multiply a number by 0, you lose information and you just can't get it back. Some matrices behave a bit like 0 and they can lose information, and these matrices will not have an inverse. So just be aware that, for example, a matrix 2, 3, 6, 9 looks quite a normal looking matrix, but there is no inverse for that matrix. You can't find any matrix that you could multiply that one by to get the identity matrix. Well, that's really enough of the theory to get us started now to have a look at how we might use this theory to solve a problem, our practical problem. And what I'm going to do now is have a look at a spreadsheet, and we can use Excel or OpenOffice, and I've chosen to use OpenOffice, but to do so I'll first formalize what we've actually going to put into our examples with OpenOffice. So let's say we've got a square matrix Q, and it's just like the quantities matrix, although I've sort of squared it up. I've taken out the sugar. I've left it the same as before, except let's say I've decided, look, I'm not going to charge people for sugar. I'm just going to leave it on the tables and they can help themselves. So I'm only going to charge for a tea, coffee, milk and biscuits. Okay, and let's say we've also got a skinny matrix B, just like the bill matrix that we had. And look, I've changed the calculations in this bill because of the fact that I'm not charging for sugar anymore. So this is the result that we would get if John had 2 cups of tea, no coffee, 2 milks and 1 biscuit. Then I'd charge him $6 for a regular, and if he was a club member I'd charge him $4.90. So basically that's the information that I'm going to use in doing our real life calculation in the spreadsheet. But before we do that, I want to look at a bit of algebra around this. There's such a thing as algebra with matrices, you probably guessed, that behaves a bit like numbers. And we can say, look, we know how the bill matrix B was created, because the quantities matrix Q was multiplied by some price list matrix P, and that gave us the B that we were ended up with. So the question now is, okay, is it possible to work backwards to discover the prices that we used in our price list matrix? Now this is quite a possible problem to have, where you know how much tea and coffee was consumed, and you know the bill that was charged, but you're just not quite sure what the prices were used to create the bill. Well, if this was ordinary algebra, you'd probably just divide both sides of that equation by Q, and you'd end up with P equals B divided by Q. Or the other thing you could do is you could multiply both sides by the inverse of Q, and you'd end up with P on its own. So let's try that with matrices. What if we take that equation which we've got in matrix form, so you've got a Q matrix times a P matrix is equal to the B matrix, and what I'm going to do is multiply both sides by something that's going to get rid of that Q. Well, the thing that's going to get rid of the Q is Q inverse. I don't know what Q inverse looks like, but if we had a Q inverse, then we could multiply both sides of the equation by Q inverse, and we'd still have a valid equation. Now, the reason I multiplied by Q inverse was so that when you combine Q inverse with Q, what you're going to end up with is the identity matrix, because that's what an inverse does. It will take a matrix and turn it back into an identity matrix. So I can replace that Q inverse times Q part of the equation with just the identity matrix. Now the good thing about an identity matrix is that it's just like the number 1. It doesn't change a matrix if you multiply it. So what I can do now is just say if I times P is equal to Q inverse times B, I can just get rid of that I because it doesn't do anything, and we're just left with P equals Q inverse times B. So that's basically a really simple way now we can use to find what the price list was that created the bill matrix B from the quantities matrix Q. We'll first need to find out what the Q inverse is, and then multiply that by the bill to come up with the price list that we're wanting to find. So let's go and do that now. What I've done is I've created a simple template in OpenOffice Calc, which is very much like Microsoft Excel, and I've actually moved the quantities from our Q matrix into that yellow matrix on the left. I'm using 2021, 1132, 2003 and 2022. That's where our Q matrix is ended up in Calc. And also on the right hand side in green, I've put the prices that were used in our bill matrix. And the formula that we've discovered, I've put in the middle here in grey, saying P equals Q inverse times B. Okay, so let's just have a bigger look at that spreadsheet now. And what I'm going to do is show you that there are some calculations already in a spreadsheet to help us work with matrices. One I've listed down the bottom there is called M inverse, and the other one is called M mult. Now M stands for matrix, and M inverse stands for give me the inverse of a given matrix, and mult stands for multiply, and M mult means give me the matrices multiplied together. So I've made some notes here to say you need to use Control plus Shift plus Enter when you're working with matrices, and that's the same with both Excel and with OpenOffice. And I've made a note here to say if you're working with mmult in Excel, you need to use a comma, but if you're using mmult with OpenOffice, you need to use a semicolon. But otherwise they're pretty much the same or very similar. So let's go ahead and do this now, this calculation. So we said we needed to find the inverse of Q inverse. So we've got Q is here. Here is what Q looks like. I'm wanting to put its inverse in this square here. I've labeled this Q inverse, I just don't know what it is. So what I'm going to do is use the formula that says equals M inverse. I'm going to open my bracket and I'm going to select the quantities matrix here. And now, before I hit enter, I'm going to press Control and Shift and hold them down while I press enter. And lo and behold, you'll see that we now have Q inverse. We didn't know what it looked like before, but now we know what it looks like. And what I'm saying here is if you take this Q inverse matrix and multiply it by the Q matrix, we should end up with an identity matrix. Okay, so we're almost ready to find the prices matrix, because according to this formula that we're going to use, the price matrix P is equal to Q inverse multiplied by the bill matrix B. Well, we've now got the Q inverse matrix, and we've now got a way of multiplying them together using the mmult formula. So let's now select where we're going to put the prices. I'm going to put them up here, and I'm going to put in equals mmult for multiply, and it's going to ask me, well, where are the two matrices that I'm going to multiply? Okay, the first one has to be Q inverse, so I'll select Q inverse. I better not select B because I've got to be in the right order, so it's Q inverse comes first, and then in order to select, before selecting the second matrix to multiply, I need to enter a semicolon, which is the thing that we use in OpenOffice, and if you were in Excel you'd be using a comma. And now I will select the second matrix, which is the B matrix for the bill, and before hitting enter I'll hold Control Shift down and then click on enter, and lo and behold you'll see that I've also now got a values for the price list that we use to create the bill. So that's an example of how we can use spreadsheets to calculate the prices using some of the theory that we developed for matrices. We've used an inverse matrix theory, and we've been able to multiply what we've found with the inverse times another matrix, the bill matrix, to arrive at the prices matrix. So lastly, to finish up this demonstration with this session, I'd like to start with, let's suppose we had our quantities matrix and we had our prices matrix and we wanted to calculate the bill. Well, this is an easy one. All we need to know is we're going to multiply Q times P to get the bill. So I'm going to type in, go to the cell where I'm wanting to put the answer, and I'm going to type in equals mmult for matrix multiplication, open bracket. I'm going to select the first matrix, I'm going to put in a semicolon, I'm going to now select the second matrix, and I'm going to hit Control, Shift and enter, and you'll see straight away that it is now come up with the bill that's required by multiplying matrices together. So that's basically the end of this session. I hope you've enjoyed it, and I'm expecting that you'll probably want to go and open up a spreadsheet and have a little play with matrices, or grab out some pen and paper and a calculator and see what you can do. So what I'd like to do now is close off, and I'm hoping that I'll be able to get some good feedback from you as to whether this has been an educational and an interesting and a fun look at an introduction to matrices. There's so much more we could have talked about with matrices, but that's just something that I wanted to do to get started. So thanks for listening, and I'll see you around. Bye.